In this video, I'm going to go over how to use the Outdoor Thermal Comfort Analysis tool. And this gives you the percent of time in comfort as an average for the analysis area and per individual analysis point for a chosen period, either annually or based on the climate analysis, looking at different months to isolate what's impactful wind versus solar radiation, for example. And the metric we're using for this is the Universal Thermal Climate Index, or UTCI, and that's a metric coming out of biology to represent the condition of a person in a space. And a good way to think of it is it's similar to the feels like temperature when you look at your weather report, where it has here's the temperature outside, which would be the dry bulb temperature, and then here's what it actually feels like. And so for UTCI, that feels like is a combination of the dry bulb temperature, the solar radiation, so both direct radiation from the sun and indirect bouncing off of buildings and the street and the ground, humidity and wind speed. And so for humidity and dry bulb temperature, we get hourly data from the weather file for um, a given climate. And so this definition looks complicated, but there's just a couple of discrete areas where you need to interact with it. There's the inputs, which I'll go over in just a second. There's the metric outputs, a little bit of customization over here. So this is essentially model prep and getting all of those four components to use UTCI that I mentioned. This is actually calculating the UTCI. This is scoring it in different ways, and then the representation over here. So first I'm going to go through the inputs and then the outputs and scoring, and then I'm going to show you example ways of presenting and interpreting this material, and talk about how you'd use a climate analysis to run this. And so if this is your first time using this analysis tool, watch this video, apply it to your project, take a first stab at that, and once you do, reach out to the environmental or UI team to have a quick discussion to review the results to make sure everything's working correctly, talk through how to interpret it and present it, and how you would get design insights out of it. And it's also important to run the climate analysis first so that the environmental team or the UI team can do that first. So let's zoom in and talk about what inputs are needed. The first one is this climate file. So we're working with the New York climate. For your given city, you're going to want to navigate to ladybug.tools EPW map here, where you can search for your city, and then when you find it, you can click on it, and this will link you to where to download the weather data. It comes with a number of file types, and what you want is the .epw file out of this. And the way you set it is you right-click, select one existing file, and you want the .epw. So I'm not going to set it now so it doesn't have to recalculate. And so that's one thing to note, is that as you're changing the inputs and or applying this to a new context, what you'll want to do first is either right-click or middle mouse click and lock the solver. And so what this does is it means you can change all these inputs. It won't automatically recalculate until you unlock it here. So you'll want to do that as you apply this to a new context. So once you have your EPW climate file set, and you'll need to set that for this example file to run correctly to start, you have date and time inputs here. This is set up to run the 15th of every month starting from 8 a.m. to 6 p.m. This is a good default to start with until you've run out a climate analysis and you understand better how the climate is changing across the year. In that case, you'll start zeroing in on certain summer months versus winter months. Down here are the model inputs. So this is a curve. It just needs to be a closed planar um, uh, polyline here. So this is showing this in here. This is set up so that you can test your building with a context. So this is the building here that we're testing. This is your static context here. And the way you set any of these is by right-clicking set one or set multiple. And it'll just let you select the geometry type that it's looking for this. And so again, once you start to set these, you want to lock the solver, set all three, unlock, and it'll recalculate. One thing that's important for this is that you want to make sure that your model is oriented correctly in terms of north. So if you've rotated your model off of north for drawing and modeling purposes, you'll need to rotate it back to get accurate results. Also, you can control the analysis cell size here, so the size of each of these, and this is whatever the document units are. You'll want to use feet or meters rather than inches or millimeters. Inches and millimeters adds a degree of resolution that's not necessary for the tool and makes it run slower. So you'll want to set this relative to your document units, and depending on how long this takes to run, you may start with a larger number as you're testing different options and then reduce it for the final run. But as an example, you'll probably never need anything that's smaller than 5 by 5 feet, and even that's pretty small. 10 by 10 feet would be just fine. One reason why you'd go lower than that is if you were testing out things like shading structures, and if they had kind of a finer resolution of the shading structure and you wanted to see the advantage, you would really increase this. So these are the initial model inputs. In the middle here, there's two other sets of inputs. This first one over here is the general characteristic of the context from kind of large, dense to fully exposed cities. And for this, what this does is this modifies the hourly wind speed coming out of the weather file. So we're not running an actual CFD here. So the wind portion of this is not responding to this specific context and massing. Solar radiation is specifically responding to this, but you choose this to modify it to generally reflect the context you're working in. So you'll want to pick and set this. Also of note here is the analysis plane height. So this is setting this up to 1.5 in terms of whatever the document units are. So in this case, we're in meters. So this is coming up to kind of person height. And so this is fine for kind of ground level outdoor spaces. But if you're starting to run this for other reasons, you can increase the height here. If you're looking at terraces, you could just set your curve to start up there, and then this would adjust for let me take this back. This is good for ground level, but if you were analyzing this terrace up here, you would want to change this to account for this height. So you do probably 17.7 meters here. And so what this is doing is it's taking the height at which the weather station data was collected, and most commonly this is 10 meters off the ground, and it's adjusting the wind to be appropriate for the height that we want it at. And so if you're analyzing terraces higher up for comfort, you're going to need to adjust this so it's accounting for the change in elevation relative to the wind speed. The other model inputs to be aware of is this comfort range. And so this is set to the UTCI standard um, of saying you're in comfort between 9 degrees and 28 degrees. So this is how this percent of time in comfort. So this green here, 70% over here is saying for 75% of the analysis period, which in this case is the full year, 70% of the year is within this comfort range between 8 a.m. and 6 p.m. So this is, keep this as the default. However, depending on the climate or the kind of city and cultural response to comfort, you might change these. That's good to discuss initially with the environmental or the UI team to see what makes sense. For example, in more extreme climates such as Shenzhen, we might increase this up to what's considered kind of a stress level of 31 or 32 if you're above that. And we're looking at the time that we're not saying that it's in comfort, but it's out of stress. So this is where you would adjust that. So those are the inputs. Mostly everything's here. There's a set of inputs to adjust and consider here. You need to adjust the wind here. You don't necessarily need to adjust these, but you should know about them. And so once we have that, we're calculating the UTCI. And so that's what this component is doing here. It's taking those different conditions that we talked about, the 4 data sources needed, and then calculating the UTCI. And so what you see here is we have 808 analysis points, and we're analyzing comfort for 132 hours throughout the year. Those represent the time range for one day a month and the hours tested there. And so what we're getting here, and you can see this is starting in January, so we're getting early morning cold, but then this is the hourly breakdown of feels like temperature. And one thing that's important to call out here is how, let's zoom in here, how UTCI determines that comfort range that we were just talking about. So from 9 to, and we're using 28, sometimes we use 26, there's this no stress category. Sometimes it makes sense given the climate to increase it to kind of moderate and slight cold stress. So you might get slightly different bounds, and then when you're out of that, you're getting kind of moderate and strong, where you start to get into danger territories. So this is a good way to understand how the thresholds were set, and then how you might start to adjust them. So we take that raw data and we format it a couple of different ways based on that comfort range that we looked at before. So the one that was over here, this 9 to 28 degrees. And so for that, we're averaging all of these analysis points. So the average for all these analysis points in this case were 60.61% in comfort for the analysis period, or that's the percent of time we're in comfort for the analysis period, which translates to 243 hours. And so just to show you, this is the total hours analyzed. So while we're doing 1 day a year, we're extrapolating that out to represent time throughout the year. So this is a direct result. This percentage is a direct result of these. It's 60% of the time. One thing that we're also doing this time of additional comfort is we're also analyzing outdoor comfort for a fully exposed point. So to say if there is nothing else around, how long is this in comfort, and so this is kind of improvement over kind of full exposure. So in this case, over full exposure, we've increased comfort by 6.25% or 152 hours. So these are metrics that you can start to use for comparison when presenting this to clients and comparing different schemes. Those are the metric outputs. Then there's this graphic output. So there's the scale over here, the visual representation. One thing to note about this is you can adjust your upper and lower bounds graphically here. So this is showing you what the bounds are for the analysis time period and what it is for the visualization. So for example, at the beginning I said anything that's in comfort for 80% of the analysis period we consider to be really good. So maybe we want our upper bound to reflect that. However, you can see since none of this gets up to 80%, it radically changes the gradient. So we're getting kind of this area in discomfort and then this area in kind of a medium comfort. So it's important to consider your ranges. You want a graphic representation where you can see difference and make decisions off of. You also want it to be representative of kind of absolute good and bad bounds. And you want to set this once and not change it because you want the graphic output and representation to be consistent across options. Because if you're changing this legend and this gradient, you can't really compare to options. And so for output, most likely it's easiest just to do a high resolution screenshot straight out of Rhino from here. But if you want the actual geometry, because this doesn't exist as geometry in Grasshopper, if you go over here, this is what's doing the representation. So you can right click, turn on and off the preview. But this up here allows you to bake the comfort map, which is the individual colored grid, and then the legend, which is over here. And so this bakes it to the layers you have specified here. So you'd want to make these layers, and then if you double click this, this will toggle it to bake it. So if you wanted to have the geometry in Rhino to do the visualization. So the last thing I'm going to go over is how you start to represent, analyze, and get takeaways, and the importance of first doing the climate analysis, which you'll want to reach out to either the environmental team or the UI team to do. And what we'll do is we'll do an annual UTCI analysis isolating for certain elements. So we understand if it's solar radiation or wind that's driving comfort, which will change how we design, but then also to know what are the areas where you have the chance through the design to either increase or decrease comfort, and when does it not matter. So what we're looking at here is a representative day for each month. So this is going from midnight to midnight. So this is the peak of the day that we're seeing here. And it's mapping different conditions. So the yellow is unshaded and no wind. So you're fully exposed to the sun and you're not getting any wind. Within the UTCI comfort ranges, so from that chart that we were looking at, this gray here, darker gray is within comfort, and then the lighter gray are your kind of expanded boundaries where you may not be comfortable for long periods, but you're generally comfortable. And so this is a way of understanding what matters when, but then also when you might be running the analysis period. So this is for New York. And so for example, if we look at March, April, and May, they're generally within the kind of the expanded comfort range. This moves a little bit down. This starts to get a little bit hot. Similarly for October or November, and maybe you're just worried about staying in comfort. So kind of April and October, no matter what you do, you're going to be staying within the comfort range. So you could eliminate these from your analysis. And then you could concentrate on the areas like, for example, June, July, August, September, where if you're exposed or unshaded, the sun really makes a difference. And so what you're seeing here is you're looking at these other ones are with shade, but either no wind or maximum wind. And you can see how little the wind actually makes a difference for comfort in the summer. It's all sun. So you could adjust the comfort range in the UTCI analysis to narrow in just on June, July, August, and September. And in that case, what you're looking at is the effects of solar radiation, and you know that the massing changes that you're doing and testing there are going to be geared towards around providing shade. And similarly, you could do it for just the winter, where maybe you're looking at January, February, March, November, and December. Sun is making a decent amount of difference, but it's positive here. It's getting into the comfort range, but then also wind makes a huge difference here as well. And so while you can run the UTCI without doing the climate analysis, if you do, you want to stick to the annual analysis, but running this gives you more nuance. So there's different ways to represent this. The plan with the time and comfort. We've given you comfort ranges here, where in InDesign you can adjust these. And it's really useful to call out particular aspects of the performance relative to the plan. And so, for example, potential plaza, could be made comfortable by sun protection. And so calling out both why things are occurring and what are approaches that can happen, and then summarizing metrics and making recommendations. So these are coming from an understanding of the climate analysis. Here's an example from a project in Houston where we ran out the climate analysis. We included things like this shading canopy here, which is providing a lot of the comfort, and then quantified how much that canopy achieved. So we ran the analysis with and without the canopy, and then we quantified the improvement. So 25% extra comfort hours. And then identified areas where we start to have discomfort, where we may need things like trees, or where positioning of certain program, like this retail here, is causing an increase in comfort. And so oftentimes it's useful to compare two options. These are just the example files, so the two same options, but you'll want to list your metrics underneath for comparison, and then annotate on top, similar to how we did in this example here, but you want to annotate what's causing the difference. So we changed this massing here, which is causing the difference, or we introduced this shading element, or we're testing for trees. And so it's really important to have this last layer of interpretation so you can relate it to design decisions and present it to the client. So again, if this is your first time, set it up, run it out, and then reach out to the environmental team or the UI team to talk about the results and troubleshoot any issues.